All right, welcome to the Explainer. Today, we're unlocking something literally game-changing, the incredible world of physical computing. If you've ever wanted to bridge that gap between digital code on your screen and the real physical world around you, you are in exactly the right place. We're going to explore how a tiny microcontroller called an Arduino acts as a digital brain, taking in information, processing logic, and triggering actual physical actions. Here's our roadmap for today's journey. Welcome to physical computing, breadboards and first blanks, mixing colors with PWM, sensing the physical world, displaying your sensor data, and finally, your next maker steps. Let's get into it. Section 1. Welcome to physical computing. Okay, let's dive into this. There's a real specific kind of magic in physical computing. It's that thrill of typing a simple line of code, hitting a button, and boom, watching a physical object right there on your desk light up, move, or make a sound. But before we can make that magic happen, we really need to understand our primary tool. Everything starts with the Arduino IDE, the integrated development environment. Think of this software as your blank coding canvas. It's the exact place where we write our instructions, compile them, and then shoot them directly into the Arduino board's memory over a USB cable. Basically, it's the ultimate translator between human logic and machine action. Moving right along to Section 2, breadboards and first blanks. Now, code alone doesn't actually light up a room, right? We've got to connect some hardware. And for that, we absolutely must start with the foundational workspace for, well, pretty much all makers, the solderless breadboard. This is your ultimate testing ground. A breadboard lets you build and prototype electronics just by pushing component legs and wires into these tiny sockets. No hot soldering iron required. This makes it incredibly safe and, honestly, so easy to fix mistakes. Put a wire on the wrong spot, just pull it right out and move it somewhere else. Simple as that. So, to actually use a breadboard, you kind of have to visualize the invisible metal rails hidden inside it. In the middle section, the holes are connected horizontally in strips of 5. Plug a wire into one of those 5 holes, and it's instantly electrically connected to the other 4. It's like a mini power grid. Then, on the outer edges, you've got these long vertical strips marked with blue and red lines. We use these continuous edge rails to distribute our 5-volt power, that's the red line, and our ground, the blue line, to all the different components across our whole project. Okay, so we have our coding canvas and we have our physical workspace. That leads us to a pretty massive question. How do we perform the iconic programmer's rite of passage in the physical world? In software, you just print "Hello World" to the screen. But in hardware, we blink an LED. To pull this off, we use the famous blink sketch. And the logic here is just beautifully simple. First up, in our setup code, we use a command called pin mode. This basically tells the Arduino, hey, we want to use your built-in LED as an output. Then, down in our main loop, we tell the Arduino to turn that LED on using the command digital write high. This pumps 5 volts to the LED, lighting it up. We tell it to wait a second, and then we hit it with digital write low to cut the power and turn it off. And it just loops forever. High, low, on, off. Boom, you're a hardware programmer. All right, Section 3, mixing colors with PWM. Now that we can blink a standard onboard light, let's totally step it up. Why just blink one boring color when we can mix millions of them using an RGB LED? To mix colors, we actually need to dim and brighten different lights. But here's the catch. Our digital pins can strictly only turn fully on or fully off. There's no in-between. To get around this, we use a super clever trick called pulse width modulation, or PWM for short. PWM essentially fakes an analog varying output by rapidly pulsing a digital signal on and off, way faster than the human eye can even process. By just tweaking how long the pulse stays on versus off, we totally control the perceived brightness. And this brilliantly illustrates exactly how we harness PWM in our code. Check out the schematic for a PWM output to an LED, and right below it, the code loops we actually use. By utilizing a simple for loop, we can incrementally increase the brightness value all the way from 0 to 255. This makes the LED smoothly fade on. Then we just reverse the loop to smoothly fade it right back off. It's a really neat effect. When we apply this exact concept to an RGB LED, which, by the way, is actually just a red, a green, and a blue LED all packaged together in one tiny bulb, we unlock a massive palette of colors. We wire the red, green, and blue legs up to Arduino pins 9, 10, and 11 because those pins specifically support PWM. Then, instead of digital write, we use the analog write command. By feeding analog write specific values between 0 and 255 for each individual pin, we can mix exact custom ratios of red, green, and blue light. It's basically digital finger painting. Let's move to Section 4, sensing the physical world. Let's see how this all builds into something even more interactive. We've totally mastered outputting light, but a truly smart system needs to take in information, right? It's time to give our Arduinos some eyes and ears by introducing sensory inputs. Think about this for a second. How exactly can we design a system that detects objects and measures their distance seamlessly in the real world without ever actually physically touching them? The answer is this awesome, incredibly popular little component, the HC-SR04 ultrasonic sensor. This clever device works literally just like a bat, using echolocation. It shoots out a high-frequency sound wave from a tiny transmitter. When that sound wave hits an object, it bounces right back to a receiver. The code then simply measures the exact time it took for that echo to return to calculate the distance. And the wiring? Super easy. Just 4 pins. Power goes to 5V, ground to ground, a trigger pin to send the pulse, let's say we put that on pin 9, and an echo pin to listen for the return on pin 10. That's the whole shebang. But you know what's truly amazing about physical computing? The sheer modularity of it all. If you don't actually need to measure distance, you can just swap out the input. Take a look at this knock sensor module. Instead of ultrasonic sound waves, this little guy detects physical impacts or vibrations. You wire its power and ground exactly the same way as the ultrasonic sensor and simply connect its S or signal port to a digital pin on the Arduino. Same core concepts, entirely different interaction. It's basically plug and play. Which brings us to section 5, displaying your sensor data. Okay, so we are gathering all this fantastic data from our sensors, distances, impacts, maybe even temperatures, but right now all that cool data is just trapped inside the computer. Let's give our project a standalone voice by adding a physical LCD display right onto our breadboard. Now, before we actually wire up a screen, we have to teach our Arduino how to talk to it. For standard I2C LCD screens, we need to install a library. That's basically a pre-written bundle of code that handles all the complex background communication for us. In the Arduino IDE, you literally just download the Liquid Crystal I2C zip file, navigate over to Sketch, hit Include Library, and click Add.zip library. Super straightforward. Thanks to that library and the I2C protocol, wiring a complex 16-character by 2-line screen only takes 4 wires. Honestly, it's amazing. Ground goes to ground, VCC goes to 5 volts, the SDA data line plugs into analog pin 4, and the SCL clock line goes to analog pin 5. But hey, pay really close attention to the code address listed here. So the crucial point is, if you upload your code and your screen is just sitting there completely blank, no need to panic. You likely just need to change the hardware address in your sketch from 0x27 to 0x3f. It's a super common quick fix. Once your display is powered up and running, you can scale your project effortlessly. Just look at this DHT11 temperature and humidity sensor. It's a dead simple 3-pin module. Power, ground, and a signal pin going straight to an analog input. You can read the live humidity and temperature data from this sensor and push it straight to your newly wired LCD screen. Boom, you've just created your own custom desktop weather station in a matter of minutes. Finally, section 6, your next maker steps. We've covered a massive amount of ground today, moving all the way from a totally blank screen to a fully wired interactive data display. As we wrap up this explainer, let's look at how to pull this entire system together for whatever you decide to build next. Because really, everything we've learned today follows one master philosophy, the sense, think, act cycle. First, you gather input from the physical world using sensors, like the ultrasonic or knock modules we looked at. Next, you route that raw data into processing, where your Arduino runs the exact logic you wrote in the IDE. And finally, you trigger an output, whether that's changing the color of an RGB LED or printing live environmental data right to an LCD screen. You now officially possess the foundational building blocks of physical computing. You actually know how to wire the hardware, write the logic, and connect the digital realm to the physical world. So I'm going to leave you with this final thought. With literally limitless combinations of sensors, code, and outputs right at your fingertips, what will you build when your imagination is the only limit? Keep tinkering, have fun with it, and I'll see you in the next explainer.